Myself A. Jagadeeswari, KSR College of Arts and Science for Women, Department of ADS, Internet of Things. IoT data link and network layer protocol. IoT devices rely on specific protocols to communicate effectively within networks. At the data link layer, these protocols establish direct communication between network nodes. IEEE 802.15.4 Foundation for Zigbee, providing low power, short range communication ideal for sensor networks. Bluetooth Low Energy BLE, designed for short range, energy efficient communications between IoT devices. Jetway, protocol for home automations with reliable mesh networking capabilities. RPL, routing protocol for low power and low-Z networks, specifically designed for IoT networks with constraint. Network encapsulations and sessions layer protocol. Thread built on IEEE provides secure and reliable mesh networking for home automations. LoRaWAN, WAN, long range wide area network protocol that enables long distance communications at low power. MQTT, message queuing telemetry transport. Lightweight, Bobley's subscribe messaging protocols designed for constrained devices and low bandwidth, high latency networks. COAP, constrained applications protocols, specialized web transfer protocols for constrained nodes in IoT networks. IoT security and service discovery protocols. DTLS, Datagram Transport Layer Security, provides communications security for datagram protocols essential for securing IoT communications. OAuth 2.0, authorizations framework enabling third-party applications to access resources with sharing credentials. TLS SSL, cryptography protocol providing communications security over computer networks. Infrastructure protocols and future trends. LWM2M, lightweight machine to machines, devices management protocols designed for sensors networks and M2M requirements. XMPP, extensible messaging and presence protocol, open standard for messaging, presence and request response services. DDS means data distribution service, real-time machines to machine protocol that provides scalable, high performance data exchange. Protocol convergence, movement towards unified standards that work across multiple platforms and use cases. Edge computing protocols, new protocols optimized for processing data closer to its source. Implements, considerations and best practice. Device constraints, match protocols to hardware limitations, power, memory and then processing. Network environment, consider bandwidth, availability, reliability and range requirements. Security requirements, evaluate encryptions, capabilities and authentications machines. Interoperability needs ensures with existing system and standards. Layer security approach, implement security at multiple protocols layers. Understanding serial communications in Arduino. Serial communications in the foundations of IoT device interaction, allowing Arduino boards to exchange data with sensors, computers and other microcontrollers. Serial communications, data transmissions 1 bit at a time over a communications channel. Serial monitor, Arduino IDE tools for sending, receiving text data. Speed of data transmissions typically 9600 bytes per second. Basic code structure. Sensors input and data processing. Arduino can collect real-world data through various sensors, forming the foundation of IoT applications. Temperature, humidity, and then light, motion, distance and example. Light means photoresistors DLS 2561, motions PIR, sensors, accelerometers, distance, ultrasonic, HC SR04 infrared, Example, reading and ultrasonic distance sensors. Wireless communications and remote controls. IoT devices often need to communicate without physical communications wireless technologies. Bluetooth, short range communications. Wi-Fi. Wi-Fi means internet connectivity. LoRa, long range low power communications. RF models, simple wireless controls. 433 MHz models. Remote controls methods. Web interfaces. Control via browser. Mobile apps custom interfaces. MQTT protocol. Lightweight messaging for IoT. Cloud platforms. ThinkSpeak. Fruit. IO. Arduino to IoT. Cloud. Project integrations and real world applications. Best practice. Start with small modular components. Text components, protocols, invisibility. Document your code thoroughly. Consider power requirements for remote deployments. Implement error handling and recovery machines. Development process. Define project requirements. Select appropriate sensors and outputs. Design communications architecture. Prototype and test individual components. Home automation and smart cities. Home automation presents one of IoT most visible applications, creating intelligence living space through connected devices. Smart thermometers that learn occupancy patterns. Security system with remote monitoring capabilities. Voice control, lighting and operations management. And then automated routeness based on time, locations or triggers. Smart cities leverage IoT networks to improve infrastructure services. Traffic management system, reducing congestion. Industrial and agriculture IoT. Agricultural IoT applications, livestock monitoring for health and location tracking. Automated irrigation system based on weather forecast. Crop diseases dedications through image recognitions. Industrial IoT. Manufacturing equipment monitoring for maintenance. Production line optimizations through real-time analytics. Quality control automations with sensor networks. Worker safety monitoring in environments. Key consideration and future trends. Implementation challenges. Security and privacy concurrence with sensitive data. Integrations with legacy systems. Scalability for large developments. Power management for remote sensors. Emerging trends. Edge computing, reducing critical applications. AI integration for predictive analytics. 5G connectivity enabling for more devices and faster responses. Standardization efforts improving interpretability. Thank you.